morning, afternoon, or evening, everyone. My name is Nindhia with the student ID number ending in 080. Today, I'll be presenting Chapter 4, Metal Alloys, Their Structure and Strengthening by Heat Treatment from Manufacturing Engineering and Technology by Kalpakjian and Skimit. This chapter focuses on how metals can be strengthened, modified, and optimized through alloying and heat treatment. We'll look at how composition, atomic structure, and thermal history determine mechanical behavior, and how engineers use these relationships to design materials for modern application. This chapter serves as a bridge between basic metallurgy and manufacturing application. It begins by explaining that metals rarely remain pure. They are almost always alloyed to improve strength, toughness, or corrosion resistance. By controlling compositions, microstructure, and heat treatment, we can engineer metals to meet the needs of structure, machinery, and high-temperature environments. This section lays the foundation for understanding how different metals are processed and treated to achieve specific performance targets. This section discusses how the structure of alloys determines their mechanical behavior. When atoms of different elements mix, they may either form a single solid solution or create distinct phases, depending on factors like atomic size and crystal structure. The degree of solubility and the phases formed influence hardness, ductility, and strength. For example, copper and nickel form a uniform solid solution with good ductility, while iron and carbon form multiple phases while widely varying properties, as we'll see later in the iron-carbon system. This slide introduces the relationship between crystal structure and mechanical behavior in metals and alloys. All metallic elements have atoms arranged in repeating geometric patterns known as crystal lattices. And the most common ones are FCC, face-center cubic, BCC, body-center cubic, and HCP, hexagonal close-packed. Each of these structures influences how easily dislocations, the effects that enable plastic deformation, can move through the lattice. FCC metals, such as aluminium, copper, and nickel, have many closely packed slip systems. This makes them very ductile and capable of sustaining large plastic strains without fracture. That's why they're used in forming operations like rolling, drilling, and depressing. BCC metals, like iron, chromium, and molybdenum, have fewer active slip systems and a larger lattice spacing, which means they're stronger but less ductile, especially at lower temperatures. For example, BCC steels tend to become brittle in cold environments, a phenomenon known as ductile to brittle transition. HCP metals, including magnesium, titanium, and zinc, have very limited slip system, so they exhibit low ductility at room temperature. However, they can be plastically deformed at elevated temperatures when additional slip systems become active. The second part of the slide reminds us that we can further modify a metal's properties through alloying, adding other elements to change atomic interactions, and through microstructural and control achieved by heat treatment. These methods can refine grain sizes, alter phase composition, or introduce solid solution and precipitation strengthening mechanisms. In essence, this slide sets up the key idea that both atomic structure and alloying work together to determine a metal's mechanical behavior, forming the foundation of the strengthening mechanisms discussed through the rest of Chapter 4. This figure provides an overview, almost like a map of Chapter 4, showing how the different concepts in this chapter are connected. We begin on the left with pure metals, which by themselves often don't have the mechanical strength or resistance needed for engineering applications. By adding alloying elements, we create alloys, combinations of metals that offer improved properties. From that starting point, the diagram branches into two major groups, ferrous alloys and non-ferrous alloys. Now that we understand how atomic arrangements affect basic properties, let's see how alloying changes those structure to enhance strength, starting with solid solutions. A solid solution forms when atoms of one element dissolves in another to create a single uniform phase. There are two main types: substitutional solid solution where solid atoms replace host atoms in the lattice. This happens when the atoms are roughly similar in size and crystal structure. A good example is brass, a substitutional alloy of copper and zinc, or copper-nickel alloys. Then there's also the second one, which is interstitial solid solution, where small atoms occupy the spaces or interstices between larger host atoms. A classic example is carbon dissolved in iron, which gives us steel. According to the Hume-Rothery rule discussed in the textbook, substitutional solubility depends on several conditions. Atomic size difference should be less than 15%. The metal should have the same crystal structure and similar electronegativity and valence. Interstitial solubility, by contrast, occurs only with very small atoms like carbon, hydrogen, or nitrogen that can fit into the small spaces of the metal lattice. These solid atoms create local lattice distortion, meaning they slightly stretch or compress the surrounding lattice, which acts as barriers to dislocation motion. Dislocations are what allows metals to deform plastically. So, by hindering their motion, the metal becomes stronger and harder. However, the trade-off is that ductility decreases, since the material becomes less able to deform before breaking. In practical terms, this is why a small addition of carbon turns soft, ductile iron into high-strength steel. This figure helps us visualize the microstructure that form in alloys. In image A, on the left, we see grains and grain boundaries representing a solid solution. For example, lead, dispersed in copper. The structure is uniform, with particles evenly distributed in a single phase. In image B, on the right, we see a two-phase system, where the light and dark grains represents two distinct composition or phases. Each phase has different mechanical and physical properties, giving the alloy a combination of strength and ductility. This diagram emphasizes that alloy performance depends not just on composition, but also on how atoms and phases are arranged within the microstructure. This table summarizes the main surface hardening process used to improve the wear resistance of steel components. Each method involves diffusing carbon or nitrogen into the surface to form a hard, wear-resistant outer layer while keeping the core tough and ductile. Now moving on, intermetallic compounds, which are materials formed by specific fixed ratios of two or more metals, such as nickel aluminide. Unlike solid solutions, which have variable compositions, intermetallics have ordered crystal structures and stoichiometric composition, meaning their atomic arrangement is very regular and predictable. Because of this order, they have high strength, hardness, and melting points. But they are also brittle, especially at room temperature. Their atomic bonding is a mix of metallic and covalent, giving them ceramic-like strength but limited ductility. These compounds are used in aerospace and high-temperature applications, such as turbine blades or jet engine components, where maintaining strength at elevated temperature is critical. This figure illustrates what happens as a pure metal cools and solidifies. In figure A, on the left, we see the cooling curve. The temperature of the liquid metal drops until it reaches the freezing temperature, where solidification begins. During this stage, the temperature remains constant, even though heat continues to be removed, because the latent heat of solidification is being released. Once all the liquid has turned into solid, the temperature resumes dropping. In figure B, on the right, we see how density changes during cooling. As the liquid solidifies, it contracts, causing solidification shrinkage. Further cooling of the solid phases causes additional but smaller shrinkage. These phenomena are critical in casting and solidification processes. Understanding how metals shrink or maintain volume during cooling helps engineers to prevent defects like porosity or cracking in cast components. This slide introduces binary phase system, which are alloys composed of two elements. They can exhibit either completely solubility, like the copper-nickel system, or limited solubility, like lead-tin or iron-carbon. Binary phase diagrams show how temperature and composition determine which phases are present. For example, in a copper-nickel alloy, the structure remains a single solid solution throughout, but in the iron-carbon system, several phases appear and transform during cooling. These diagrams are the foundation for understanding alloy behavior, solidification, and microstructure formation. Next, we'll look at one of the most important transformations in binary system, the eutectic reaction. This slide explains the eutectic reaction, which occurs when a liquid transforms into two solid phases at a specific temperature and composition. The lead-tin system is a classic example, forming a fine, alternating lamellar structure at 183 Celsius. Eutectic alloys are widely used for soldering because they melt and solidify sharply at a single temperature, ensuring clean and uniform joints. The microstructure procedure is fine-grained, providing a good balance of strength and ductility. Now that we understand eutectic reaction, let's examine the most important metallurgical system, the iron-carbon system. The iron-carbon phase diagram is the most essential in metallurgy, describing how iron and carbon combine to form steels and cast irons. At 0.77% carbon and 727 Celsius, austenite transforms into ferrite and cementite, producing perlite, a layered microstructure of soft and hard phases. Steels contain less than 2% carbon, while cast iron contains more. This diagram forms the basis of all heat treatment processes, including annealing, normalizing, quenching, and tempering. Next, we'll look more closely at the individual phases present in the system and their roles. This slide shows how carbon content is the key factor in classifying steels and directly influences their mechanical properties. Low-carbon steels, with less than 0.3% carbons, are ductile, malleable, and easily weldable. They are commonly used for automotive panels, structural shapes, and general fabrication because they are easy to form. Medium carbon steels, containing about 0.3 to 0.6 carbon, offers a balanced medium strength and ductility. They can be heat treated to improve hardness and are often used for gears, axles, and machinery parts. High carbon steels, with more than 0.6% carbon, are very hard and wear resistant, making them ideal for tools, cutting edges, and springs, though they are less ductile and harder to weld. In summary, as carbon content increases, strength and hardness go up, but ductility and weldability decreases. This simple classification helps engineers choose the right steel for their job. This figure shows the binary phase diagram for the nickel-copper system, which is an isomorphous alloy, meaning the two elements are completely soluble in both liquid and solid states. On the left side, we have pure copper, and on the right, pure nickel, each with its own melting point. The diagram's liquidus and solidus lines define the temperature ranges where solidification occurs. Between those two lines lie a two-phase region, where both solid and liquid phases coexist during cooling. The circles on the right illustrate what happens during solidification. The top circle shows the nucleation of crystal as cooling begins. The middle circle represents the growth of dendrites or tree-like crystals, and the bottom circle shows the fully solidified structure with visible grain boundaries separating the crystals. This system demonstrates how uniform solid solutions like NiCu solidify smoothly, producing homogeneous microstructures with consistent mechanical properties, ideal for corrosion-resistant applications like coins, marine hardware, and heat exchangers. This slide lists how alloying elements modify steel behavior. Nickel and magnesium stabilizes austenite and improve toughness. Chromium, molybdenum, and vanadium forms carbides, increasing hardness and wear resistance. Silicon strengthens ferrite and enhances oxidation resistance. And carbon remains the primary element controlling hardness. These elements not only alter transformation temperatures but also affect the microstructure's final form, making alloy steels more versatile than plain carbon steels. Next, we'll explore how microstructure actually changes during heat treatment using time-temperature diagrams. Elements such as nickel, Ni, manganese, Mn, chromium, Cr, molybdenum, Mo, silicon, Si, vanadium, V, and tungsten, W, shift phase boundaries and influence transformation temperatures. This means they can control how and when different structures, like ferrite, austenite, or martenite, form during heating and cooling. Focusing on austenite formers, nickel and manganese, along with additional carbon, expand the austenite region in the iron-carbon diagram. They lower the eutectoid temperature, making it easier for austenite to form during heat treatment. These elements also increases hardenability, helping steels achieve uniform hardness after quenching. Additionally, they improve toughness and ductility, especially in steel designed for low temperatures or impact-resistant applications, such as cryogenic tanks or structural steels used in cold climates. Now that we've discussed austenite formers, the slide focuses on ferrite stabilizers and carbide formers as well as their effects on steel behavior. Elements such as chromium, molybdenum, vanadium, and tungsten stabilize the body center cubic ferrite structure and promotes carbide formation. These carbide provides excellent high temperature strength and wear resistance, making them essential in tool steels and cutting applications. However, in excessive amounts, they can also reduce ductility and toughness. Silicon has a different role. It promotes graphite formation in cast iron, acts as a deoxidizer during steelmaking, and slightly strengthens ferrite through solid solution effects. Carbon remains the primary strengthener in steels. When combined with alloying elements, it forms complex carbides, which significantly enhances hardness and wear resistance. When it comes to hardenability, elements such as Mn, Cr, Mo, Ni, and W help austenite form deeper below the surface during quenching, an important factor for thick or high-performance parts. Finally, solid solution strengthening and precipitation hardening further refine the structures. Elements like NiCu and Ai occupy lattice sites or form fine precipitates that blocks dislocation motion, increasing overall strength. In practical design, alloy selection is always about balance between strength, ductility, corrosion resistance, cost, and heat treatability. Each heat treatment schedule must be adjusted to composition to produce the intended microstructure and mechanical properties. Next, these are the figures for the example of tensile strength, yield stress, hardness, and elongation. These mechanical properties of copper nickel and copper zinc alloy as a function of their composition. The curves of zinc are short because zinc has a maximum solid solubility of 40% in copper. Cast irons, typically containing 2.1 to 4.5% carbon, are known for their excellent castability and vibration damping. The form of carbon graphite or semonite defines the iron's type and properties. Gray iron contains graphite flakes, providing good machinability but low tensile strength. Ductile or nodular iron, shown in figure 4.13b, has spherical graphite nodules that greatly improve toughness. White iron contains semonite and is extremely hard, while malleable iron results from heat-treated white iron, improving ductility. Compact graphite iron (CGI) combines features of both and is widely used in modern engine blocks. Now this is another example of the iron-iron carbide phase diagram. Heat treatment is one of the most important processes used to modify the properties of ferrous alloys, mainly steels. The transformation in heat treatment are based on how austenite, which is a high-temperature phase of steel, decomposes into other structures as it cools. The key transformations are, first, perlite. It is formed by slow cooling of austenite It has alternating layers of ferrite and cementite, and this gives it a moderate hardness and strength, a good balance for structural uses. Second, there is sphaeriodite, produced by heating perlite or bayanite just below the eutectoid temperature for a long time. Cementite forms rounded particles instead of layers. This structure offers high toughness and ductility, ideal for machining or forming. The third, bayanite, formed at an intermediate cooling rate between perlite and marzenite. It has a fine microstructure, giving it higher strength than perlite while still maintaining some ductility. The fourth, marzenite, created by very rapid cooling or quenching from the austenite phase. The carbon atoms are trapped, forming a hard but brittle structure. It's the hardest phase but lacks toughness. And 5, tempered marzenite. To improve marzenite's brittleness, we reheat it below the eutectoid temperature. This tempering process allows some carbon diffusion, producing a microstructure with balanced strength, hardness, and toughness. It's commonly used in tools and mechanical parts that need both strength and durability. And here are the figures for examples of what we just talked about before. On the very right, for A, is austenite, ferrite, marzenite, and carbon. Unit cells. This is the effect of percentage of carbon by weight on the lattice dimensions for marzenite is shown on D. Next, let's look at time-temperature transformation diagrams, also called TTT diagrams or isothermal transformation diagrams. These diagrams show how the microstructure of steel changes over time when held at a constant temperature. So what the diagram shows. The TTT diagram plot temperature on the vertical axis and time on the horizontal axis. They describe how austenite transforms into other phases like perlite, bayanite, or marzenite, depending on how fast it cools. From start to finish and 50% curve. The start of the curve shows when transformation begins, roughly at 0%. The finish curve shows when transformation is complete, around 100%. Between these two is the 50% transformation curve, which is useful to estimate how fast transformation happens at each temperature. The nose of the curve is the most important feature of the whole TTT, the point of fastest transformation. During quenching, the cooling path must pass to the left of the nose to avoid forming perlite or bayanite and instead form marzenite. If cooling is too slow and passes through of the nose, you'll get perlite or bayanite instead of marzenite. The critical cooling rate is the minimum speed needed to bypass the nose of the curve. If cooling is faster than this rate, marzenite forms. If it's slower, you'll end up with perlite or bayanite instead, which are softer structures. So, what's the difference between a TTT diagram versus a CCT, continuous cooling transformation diagram? In short, the TTT diagram are theoretical and helps explain transformation behavior. CCT diagrams are practical. They guide real-world heat treatment process by showing how cooling rate affects the microstructure and properties. The geometry test measures a steel's hardenability, its ability to form marzenite at different depths when quenched. A heated cylindrical sample is quenched with water at one end, creating a gradient of cooling rates. Hardness is then measured along this length. The farther from the quenched end, the slower the cooling. Alloy steels with elements like CRMO and Ni retain hardness deeper into the part, while plain carbon steels harden only near the surface. This test helps engineers predict how a part will respond to real heat treatment. The purpose of the end-quench hardenability test is to provide a standardized measure of hardenability to alloys so it can be compared and heat treatment schedules designed. The procedure is first, the austenite specimen is at the end at the specific temperature and hold to homogenize. Then it's transferred to the Germany device and apply the water jet to one end. After cooling, measure hardness, Rockwell or Vickers, at fixed intervals for the quenched end. For example, it could be at every few millimeters. Then the fourth, plot hardness versus distance from quenched end. This is the Germany curve. Now this is another one of those schematic illustrations of the microstructure for an iron-carbon alloy of eutectoid composition. This one is 0.77% carbon. Above and below the eutectic temperature of 727 Celsius or 1,341 Fahrenheit. Non-ferrous alloys such as aluminum, copper, and titanium do not undergo the same transformation as steel. Instead, they are strengthened by strain hardening, solid solution strengthening, and especially precipitation hardening. These processes improve yield strength without significantly increasing weight, which is why aluminum and titanium alloys are widely used in aerospace and transportation. Now we move on to solution treatment, which is the first step in the heat treatment of many non-ferrous alloys, especially aluminum alloys. Heating stage. The alloy is heated to a temperature where the solid atoms like copper, magnesium, or zinc completely dissolve in the matrix. For aluminum alloys, this temperature is usually between 500 and 550 Celsius. At this stage, the structure becomes homogeneous, with the solid atoms evenly distributed. Moving on to the quenching stage. After heating, the alloy is rapidly quenched, usually in water. This traps the solid atoms in place before they can precipitate out. As a result, we form a supersaturated solid solution, which is metastable, meaning it's not in equilibrium but temporarily stable. This metastable structure is important because it's the starting point for precipitation hardening or age hardening. Later, when the alloy is aged, tiny precipitates form, strengthening the metals. For example, in the ALCU system, the alloy is solution treated at around 540 Celsius. It's then quenched quickly to retain the copper atoms dissolved in the aluminum matrix. This prepares the alloy for the next stage, aging, where those copper alloys will form fine precipitates that increases strength. Moving on, let's look at stainless steels and heat treated. How stainless steels are heat treated. There are three main types: austenitic, marstensitic, and ferritic, and each respond differently to heat treatment. Austenitic stainless steels are the most common type, like the 304 and 316 grade. They're heated to around 1,050 Celsius for solution treatment. This dissolves any carbides they may form during service or processing. After heating, they're quenched rapidly to retain the austenitic structure. Sometimes elements like titanium or niobium are added for stabilization. This prevents steinization, which is when chromium carbides form at grain boundaries and reduces corrosion resistance. Marstensitic stainless steels. These are the hardenable grades, often used for knives, turbines, or tools. They are first austenized, then quenched to form martenite, giving them high hardness. However, they are brittle, so they are tempered afterwards to improve toughness and ductility. Third, ferrite grades, on the other hand, can form martenite because of their low carbon content. They are annealed instead. This process refines the grain structure and relieves residual stresses from fabrication. This helps maintain good corrosion resistance and mechanical stability. In general, heat treatment of stainless steels improve corrosion resistance, strength, and toughness. The final properties depend on the chromium and nickel contents. Chromium provides corrosion resistance, while nickel stabilizes the austenite phase. This is a figure of the example of a microstructure of perlite in the 1080 or 1080 steel, formed from austenite to eutectoid composition. The lighter regions are ferrite and the darker regions are carbide. Moving on, we're going to move on to 4.10, which is case hardening. We're going to start with carburizing. The purpose of this is to add carbon to the surface of low carbon steel to increase hardness and wear resistance. The process starts with steel is heated to 870 till 950 Celsius in a carbon-rich atmosphere, gas, liquid, or solid form. Carbon diffuses into the surface, creating a high carbon outer layer, or the case. The part is then quenched to form martenite at the surface. This results in hard surface at around 55 till 65 HRC, tough core, case depth of 0.5 till 1.5 millimeters. These applications are useful for gears, cams, shafts, bearings, and clutch plates. Next, nitriding. The purpose of this is it introduces nitrogen into the surface to improve hardness and fabric strength without quenching. First, they are carried out at 500 till 600 Celsius or 925 till 1100 Fahrenheit in ammonium gas atmosphere. This forms hard nitride compounds, for example, aluminium, chromium, molybdenum, and nitrites. This results in a very hard surface, up to 1100 HV, case depth of 0.1 till 0.6 millimeters, and minimal distortions. The application is used for gears, shafts, valves, clusters, and pump fuels parts. Now, carbonitriding, and cyaniding. The purpose is to add both carbon and nitrogen for enhanced surface hardness and wear resistance at lower temperature than carburizing. It is performed at 700 till 800 Celsius in an atmosphere of carbonaceous gas and ammonia, flowed by oil quenching. This results in surface hardness of 55 till 62 HRC, case depth of 0.07 till 0.5 millimeters, less distortion than carburizing, and it's used in bolts, nuts, small gears, and machine parts, heating the toughness. Cyaniding produces a thin, hard case by simulatingly introducing carbon and nitrogen using molten cyanide salts. The seal is heated to 760 till 845 Celsius in a molten sodium cyanide bath. The carbon and nitrogen diffuses into the surface, then the part is quenched. This results in a hard surface up to 65 HRC, case depth of 0.025 to 0.25 millimeters. Quick process but hardest due to cyanide use. It's used for bolts, nuts, screws, and small gears. Now we'll discuss annealing, a heat treatment process used to improve ductility and relieve internal stresses in metals. It's one of the most common treatments in manufacturing, especially after cold working or machining. Annealing involves heating the metal to a specific temperature, holding it there for a certain time, and then cooling it slowly. The main goal is to make the metal softer, more ductile, and less brittle by allowing internal structure to recover. There are different types of annealing. There is full annealing, which the metal is heated above the weak crystallization temperature, allowing complete weak crystallization of the grains. This produces a coarse, uniform structure with maximum softness, ideal for improving formability. It's commonly used for steels before machining or shaping. There is process annealing, where the metal is heated to a lower temperature below full recrystallization. It allows partial recovery of ductility after a light cold working, and is often used in sheet metal manufacturing to restore formability before rolling steps. Stress relieving. This process involves heating the metal below the recrystallization temperature just enough to relieve internal stresses. It's mainly used to remove stresses caused by machining, welding, or cold working, preventing distortion or cracking. Next, normalizing. In this process, the material is heated above its critical temperature and then air-cooled. It refines the grain size and helps homogenize the structure. Normalized steels become tougher and stronger than fully annealed ones. Next, we are going to talk about it one by one, the first being recovery phase. The recovery phase occurs when a cold work metal is heated to a relatively low temperature, below the recrystallization point. During recovery, the dislocation caused by plastic deformation rearrange themselves into lower energy configurations. The internal stresses are partially relieved, but the grain structure remains the same. The effects is electrical and thermal conductivity improves. However, mechanical properties such as hardness and strength change very little. This stage mainly helps stabilize the metal before heating. moving on to the recrystallization phase. The recrystallization happens when the temperature is increased above the recrystallization temperature. New strain-free grains form and replace the old deformed grains from cold working. This process completely removes the effects of strain hardening. The effect is that the metal becomes softer, more ductile, and easier to shape. The recrystallization temperature depends on the amount of prior deformation. The more the metal is cold worked, the lower the temperature needed, and is commonly used after cold rolling or drawing to restore workability. Grain growth. If heating continues after recrystallization, grain growth begins. Larger grains form as smaller grains are consumed, reducing the total grain boundary area. While larger grains reduce strength and hardness, they improve ductility and creep resistance. Therefore, grain growth must be controlled excessively. Growth can make metals weaker and less uniform. This figure shows 3 types of cast iron microstructures under a magnification of 100 times. A. On the very left, ferritic gray iron. In image A, we see ferritic gray iron where graphite appears in flake form. These graphite flakes act as stress concentrators, which makes gray iron brittle. However, gray iron has excellent damping capacity and good machinability, making it useful for engine blocks, machine bases, and brake discs. In image B, in the middle, we have ferritic ductile iron, also called as nodular or spheroidal graphite iron. Here, the graphite forms in rounded nodules instead of flakes, greatly reducing stress concentration. This gives ductile iron higher strength, toughness, and ductility than gray iron. It's often used for crankshaft, gears, and heavy-duty machine parts. On the very right, in image C, we see ferritic malleable iron. This material originally solidifies as white cast iron, where the carbon is present as cementite. It is then heat treated to convert cementite into graphite clusters or temper carbon. This process produces a tough and ductile material, commonly used in fittings, brackets, and automotive components. Heat treatment requires furnaces designed to accurately control temperature, heating rate, and atmosphere. These systems are essential to ensure uniform properties, prevent oxidation, and achieve desired microstructures. There are several types of furnace used, depending on the process and part size. Common types include batch furnaces, continuous furnaces, vacuum furnaces, and salt bath furnaces. Batch furnaces are used for small or varied loads, while continuous furnaces are ideal for mass production. Vacuum and controlled atmosphere furnaces are used when oxidation or contamination must be avoided. The key equipment to consider is the uniform temperature distribution, accurate control of heating and cooling cycle, and proper handling system for quenching and transferring parts. The furnace atmosphere plays a key role in controlling surface reaction during heating. A properly controlled atmosphere prevents oxidation, decarburization, or carbon loss from steel. There are types of atmospheres: neutral atmosphere, example nitrogen or argon, which prevent oxidation. Reducing atmosphere, for example as hydrogen or carbon monoxide, helps remove oxides. And carburizing atmosphere, for example methane or propane, add carbon to the surface for case hardening. The benefit is that by controlling the gas composition, we can tailor surface properties, improve finish, and ensure consistent hardness. Moving on, specialized processes. Certain specialized heat treating systems are designed for high precision or special alloys. For example, vacuum furnaces are used for superalloys or reactive metals to prevent contamination. Fluidized bed furnaces provide uniform heating through fine suspended particles. Induction heating system use electromagnetic fields for rapid localized heating. Laser and electron beam surface hardening offer precise controlled surface treatment without affecting the bulk material. These methods allow better temperature control, faster heating, and reduced distortion, critical for high-performance components. Now, figure 4.14 is an example of a microstructure of a euclitoid steel. It is formed by tempering the steel at 700 Celsius. Before performing heat treatment, we need to carefully consider a few key design factors. First, geometry. Avoid sharp corners or a sudden thickness change, since they cause uneven heating and stress buildup. Second, uniformity. Design parts with consistent cross-section so they cool evenly and don't wrap or distort. Next, surface finish. Smoother surface reduces stress concentrations and lower the risk of cracking during quenching. Material selection is also critical. Choose alloys with the right hardenability and machinability for the process. Finally, quenching media. The cooling medium, whether it's water, oil, polymer, or gas, must be chosen based on how fast you need to cool the part and how much distortion you can tolerate. By considering all these factors, we ensure that the heat treatment produces uniform hardness, minimal distortion, and reliable mechanical properties. During heat treatment, preventing defects and maintaining dimensional accuracy are critical. First, to prevent defects. Preheating the material helps reduce the thermal gradient before quenching, which minimizes cracking or distortion. Agitating the quenching medium, like stirring oil or water, ensures uniform cooling across the surface. Finally, after heat treatment, inspection steps such as hardness testing and dimensional checks confirm that the part meets required properties and tolerance. Next, for industrial consideration. Proper fixturing supports the parts and prevents warping during heating and cooling. For a complex component, we can simulate thermal stresses using finite elements models to predict deformation before processing. And lastly, performing controlled tempering after quenching helps relieve residual stresses and stabilize dimension, ensuring long-term reliability and performance. In short, careful process control and simulation tools are key to produce defect-free, dimensionally stable heat-treated parts. To wrap up Chapter 4, let's review the key ideas. We began by looking at alloy structures, including solid solutions, intermetallics, and multi-phase system, which form the foundation for understanding metallic materials. Then, we covered phase diagrams, especially the iron-carbon system, which helps guide the design and control of steel microstructures. We also explored heat treatment methods such as annealing, quenching, and tempering, each of which tailors microstructures to achieve desired mechanical properties. Next, we saw how hardenability and precipitation hardening are vital for achieving strength and durability in engineering applications. Processes like case hardening and the use of controlled atmosphere enhance surface hardness and wear resistance. Finally, good design practice and furnace control ensures safety, uniformity, and high-quality results across industrial operations. In short, Chapter 4 shows how understanding structure, heat treatment, and process control allows us to engineer metals with the exact combination of properties we need. That concludes my presentation on Chapter 4 of metal alloys and their strengthening by heat treatment. I'd like to apologize in advance for any mistakes or misinformation that might have appeared in my explanation. And thank you so much for your time and attention. Bye!